You are staring at an empty patch of the ocean floor. The water is perfectly clear, the sunlight filtering down and shifting, fragmented nets of gold. There's a scatter of crushed coral, a faint shadow cast by a passing current, and nothing else. You blink. The shadow does not move, but the sand itself seems to inhale. In an instant, the emptiness fractures. The coral rubble dissolves. The texture of the seabed falls away. What was once empty space erupts into a living, breathing entity. It does not arrive from somewhere else. It simply decides to let you see it. This is a cuttlefish, an animal that does not hide within its environment, but actively edits reality to erase its own existence. When we think of camouflage, we usually imagine a creature wearing a disguise, a moth mimicking a dead leaf, a predator wearing the colors of the dry savanna. But that is passive. That is a costume. What the cuttlefish does is something far more profound and far more unsettling. It does not wear a disguise. It manipulates the fundamental physics of light. It becomes a living screen, projecting a calculated distortion of the world so perfect that the observer's brain simply deletes the animal from its visual field. To understand how this is possible, you have to look past the surface of the animal and into the microscopic architecture of its skin. This is not ordinary biological tissue. It is a multi-layered optical technology that operates with a precision we are only just beginning to replicate in our most advanced engineering. The outermost layer of this living cloaking device is made up of millions of microscopic organs called chromatophores. Imagine tiny elastic sacs filled with dense pigments, black, brown, red, yellow. Each one of these sacs is tethered to a ring of radial muscles, and every single muscle is wired directly into the animal's nervous system. In a fraction of a millisecond, the cuttlefish can fire an electrical impulse that forces those muscles to contract, pulling the pigment sac wide open like a drawn curtain. Or it can relax the muscles, shrinking the color down to an invisible microscopic dot. Millions of these firing in perfect synchrony allow the animal to paint its skin with moving colors faster than the blink of an eye. But color is only the first deception. Color alone cannot fool the complex eyes of the reef. Beneath the chromatophores lies a second layer, composed of structures known as iridophores. These do not contain pigment. Instead, they are made of microscopic, stacked plates that act like living prisms. They don't generate color. They manipulate the light that hits them, reflecting specific wavelengths through constructive interference. By shifting the angle and spacing of these plates, the cuttlefish can bounce back an iridescent shimmer, blues, greens, and silvers that perfectly mimic the dancing light of the shallow waters. And deeper still lies a third layer, the leucophores. These are broadband reflectors. Their sole purpose is to capture the ambient light of the environment and scatter it back out in every direction. If the water is murky and green, the leucophores reflect a diffuse, murky green. If the water is crystal clear, they reflect bright, white light. They allow the cuttlefish to match not just the color of its surroundings, but the exact brightness and spectral quality of the space it occupies. But the cuttlefish's manipulation of physics goes even further, stepping into a realm of vision that humans cannot even perceive. The sunlight penetrating the ocean is polarized, its light waves oriented in specific directions. While human eyes are completely blind to this polarization, many marine predators and prey rely on it as a secondary layer of vision, allowing them to spot the subtle, hidden outlines of transparent or camouflage creatures. The cuttlefish knows this. It actively tunes the reflective layers of its skin to match the exact polarization of the water around it. To the polarized eyes of a passing shark, the cuttlefish does not just blend in. Its visual signature is completely flatlined. It erases itself across multiple sensory dimensions simultaneously. Yet, all this biological hardware would be useless without the software to run it. And the mind of the cuttlefish is perhaps the most terrifyingly efficient processing engine in the invertebrate world. It has a massive, highly centralized brain dominated by enormous optic lobes. When a cuttlefish surveys its environment, it isn't just looking at the scenery. It is instantly performing a complex statistical analysis of the world. It calculates the contrast of the rocks, the spatial frequency of the sand grains, the angle of the shadows, the sharp edges of the coral. And then, without any conscious delay, it maps that mathematical data directly onto its own skin. There is no gap between perception and transformation. The cuttlefish sees, and the cuttlefish becomes. The observer and the environment are collapsed into a continuous, real-time feedback loop. If it moves over a field of complex, chaotic coral, it instantly deploys disruptive coloration. It generates harsh, high-contrast bands of black and white across its body, breaking up its outline so severely that a predator's brain cannot mathematically connect the shapes into a recognizable form. If it glides over a smooth, sandy bottom, the high contrast vanishes, replaced by a soft, uniform stippling that mimics the exact grain size of sand below. But true invisibility requires more than just color and light. The ocean is three-dimensional, and a flat image painted on a smooth body will still cast a shadow. So, the cuttlefish reshapes its own flesh. Covering its body are bundles of specialized muscles called papillae. With a thought, the cuttlefish can flex these muscles, forcing its smooth skin to erupt into spikes, bumps, ridges, and fleshy fronds. It can physically sculpt its body to mimic the exact jagged texture of a piece of coral or the soft, drifting fronds of seaweed. It becomes a topographical map of its surroundings. We tend to think of camouflage as a defensive mechanism, a way for the weak to hide from the strong. But for the cuttlefish, invisibility is a weapon. When it shifts from prey to predator, its mastery of light takes on a much darker, psychological role. Imagine a small crab, highly alert, scanning the reef for danger. The cuttlefish does not sneak up on it from the shadows. It glides out into the open, completely exposed, and then it begins to strobe. Dark and light bands begin to pulse across the cuttlefish's face and tentacles, rolling outward in rhythmic, hypnotic waves. This is known as dynamic camouflage, but to the prey, it is sensory overload. The rapidly shifting patterns completely overwhelm the crab's neural circuits. Its brain tries to process the conflicting visual data, trying to calculate the speed, direction, and shape of the object in front of it, and it fails. The crab's nervous system essentially crashes. It freezes, locked in a state of perceptual paralysis, mesmerized by the strobing lights. In that single moment of hesitation, the cuttlefish strikes. Two hidden feeding tentacles, tightly coiled inside its arms, shoot forward with explosive, blinding speed. The suction cups lock onto the disoriented prey, and it is dragged backward into a sharp, crushing beak. This is informational warfare. The cuttlefish does not defeat its prey with physical strength. It defeats them by hijacking their cognitive processing. It feeds them corrupted data, crashing their ability to make a decision. In the predator-prey dynamic, there is usually a clear asymmetry. One animal hides, the other seeks. The cuttlefish shatters this rule. It controls both sides of the equation. It dictates exactly what other animals are allowed to see and exactly how they are allowed to perceive it. It is a master of psychological manipulation, turning visibility into a sliding scale that adjusts at will. But this godlike control over reality comes with a heavy price. Maintaining this level of deception is exhausting. The continuous firing of millions of muscles, the rapid calculation of the visual environment, the physical distortion of the skin, it requires a massive, constant drain of metabolic energy. A cuttlefish cannot sustain high-intensity, hyper-accurate camouflage indefinitely. It must constantly weigh the cost of its invisibility against the immediate threat level. There are times it must let the illusion fade, resting its neural grid and relying on simpler, less demanding patterns, hoping it is not noticed in its moment of recovery. Furthermore, the cuttlefish's greatest weapon is entirely dependent on something outside of its control, the health of the reef itself. The cuttlefish does not invent its camouflage from nothing. It requires a template. It needs the vibrant, chaotic, broken visual landscape of a healthy ecosystem to hide within. If the reef dies, if the coral bleaches white, if the structural complexity crumbles into flat, barren rubble, the cuttlefish loses its canvas. In a degraded, uniform environment, its ability to generate disruptive patterns becomes useless. It becomes conspicuous. It becomes vulnerable. Its invisibility is not a solitary achievement. It is co-produced by the environment. The reef provides the data, and the cuttlefish acts as the mirror. Without the complexity of its home, the illusion shatters. This creates a beautiful, yet brutal evolutionary arms race. For millions of years, the cuttlefish has refined its optics, its neurology, and its muscular control to become the ultimate ghost of the ocean. But the predators that hunt it are not static. Their eyes have evolved to look for the tiny, microscopic flaws in the illusion, a slight mismatch in texture, a rhythm of movement that doesn't quite match the surge of the current, a failure to perfectly align the polarization. The cuttlefish lives on a razor's edge. It exists in a permanent state of negotiation with the light, the water, and the minds of the creatures around it. It is an improviser trapped on a stage where the penalty for a single bad performance is death. It is a creature that proves that reality is entirely subjective. What we see is not necessarily what is there, but merely what our brains are capable of processing. The cuttlefish exposes the vulnerability of the eye and the easily hacked nature of the mind. It doesn't just vanish into the dark. It stands in the bright, piercing sunlight of the shallow seas, rewrites the light waves bouncing off its skin, and quietly erases itself from the world. The open ocean is a realm defined by its emptiness. When you stare into the blue column, stretching endlessly in every direction, the mind attempts to find boundaries that do not exist. There are no walls, no substrate, no structures to anchor the eye. In this environment, survival is dictated by a simple rule. If you can be seen, you can be eaten. Predators constantly scan the void for the slightest interruption in the uniform blue. A shadow, a flash of silver, a sudden contrast. Prey animals spend their entire lives trying to minimize that contrast, attempting to blend into the endless gradient of light. Every organism in the pelagic zone is locked in a constant, exhaustive game of visual chess, reacting to movement, calculating distances, and preparing for the chase. But what happens when a predator simply refuses to play the game? Imagine a small fish drifting through this seemingly empty space. Its sensory world is highly tuned. Its lateral line detects the faint pressure waves of distant currents. Its eyes filter the scattering light, searching for the sharp outline of an approaching threat. It is vigilant, it is prepared, and it is completely, hopelessly unaware that it has already made a fatal miscalculation. The water ahead of it appears completely clear. There is no ripple, no shadow, no tightening arc of pursuit, but suspended within that perfect clarity, hovering with absolute indifference, is a gelatinous cube. The fish swims forward, feeling perfectly secure. It does not flee, because there is nothing to flee from. And then, as it crosses a boundary that cannot be seen, the water itself seems to tear it apart. This is the box jellyfish. It is an organism that has taken the concept of invisibility and pushed it to its absolute, terrifying extreme. It does not hide. It does not camouflage itself against the background. It achieves something far more profound: optical minimalism. It reduces its visual signature so flawlessly that it effectively ceases to exist within the perceptual field of other living things. It is a predator that turns the very medium of the ocean into a weapon. When you look at the architecture of the box jellyfish, it defies everything we associate with a lethal apex predator. There are no crushing jaws. There are no razor-sharp claws. There is no centralized brain calculating the trajectory of an attack. There is no heavy musculature built for explosive speed. Its body is almost entirely composed of water, encased in a fragile, transparent bell that seems more like a structural anomaly than a biological threat. It is a ghost, drifting on the currents, seemingly devoid of intent. Yet, within this fragile, floating bell lies one of the most sophisticated, precise, and devastatingly lethal delivery systems ever evolved on this planet. To understand the true horror and brilliance of the box jellyfish, you must look past its transparent bell and focus on the deadly tendrils trailing beneath it. These tentacles, which can stretch for meters into the abyss, are functionally invisible in the shifting light of the ocean. They drift like microscopic spiderwebs, creating a vast, three-dimensional minefield in the open water. But it is not the tentacles themselves that kill. It is what they carry. Lining the surface of every single tentacle are millions of microscopic, specialized organelles called nematocysts. You can think of each nematocyst as a highly pressurized, coiled spring. Inside each microscopic capsule is a hollow, harpoon-like filament, bathed in a potent cocktail of venom. These are not muscles that contract. They are pneumatic weapons, operating on physical pressure that borders on the impossible. The internal pressure within one of these capsules is staggering, held back by a microscopic trigger that waits for the perfect moment. And the trigger mechanism is a masterclass in biological engineering. If the jellyfish fired its harpoons every time a piece of floating debris or a grain of sand brushed against its tentacles, it would exhaust its arsenal in minutes, wasting precious metabolic energy. To solve this, the box jellyfish has evolved a dual-filter security system. The nematocyst requires two distinct signals to deploy. First, there must be tactile stimulation, the physical pressure of something brushing against the tentacle. But that alone is not enough. The second signal is chemical. The surface of the tentacle must detect specific proteins and chemical signatures that belong exclusively to the skin or scales of living prey. When both of these conditions are met, when the fish brushes the invisible thread and the chemical lock is engaged, the system fires. The discharge of a nematocyst is one of the fastest mechanical events in the entire animal kingdom. The harpoon accelerates with a force that defies comprehension, shooting outward in a fraction of a millisecond. It moves so fast, with such violent acceleration, that it effortlessly pierces protective outer layers of the prey. Millions of these harpoons fire in perfect, explosive synchrony, driving deep into the tissue and injecting their payload directly into the bloodstream. This is not a gradual poisoning. This is an instantaneous biological shutdown at the cellular level. The venom of the box jellyfish is a biochemical nightmare, a complex arsenal of proteins and peptides designed to completely overwhelm the prey's physiological systems in seconds. It contains specialized toxins that immediately attack the ion channels in nerve and muscle cells. In a healthy animal, these channels open and close to transmit electrical signals, allowing the brain to communicate with the body. The jellyfish venom wedges these channels open, causing a massive, catastrophic flood of electrical noise. The prey's nervous system is instantly short-circuited. Paralysis is immediate. But the venom does not stop there. It contains cardiotoxins that target the heart muscle with terrifying speed. They alter the rhythm and strength of the heartbeat, causing the cardiovascular system to violently falter and collapse. The fish does not have time to register the pain. It does not have time to thrash or trigger an escape reflex. The moment of contact is the exact moment of its incapacitation. In the vast, open ocean, where prey can flee in any of three dimensions, speed is usually the ultimate currency. Predators invest massive amounts of energy into swimming faster, turning sharper and enduring longer chases. The box jellyfish bypasses this evolutionary arms race entirely. It does not evolve speed, it evolves absolute immediacy. It collapses the delay between detection and death to near zero. Because it is so perfectly transparent, the prey never goes through the standard sequence of predator interaction. There is no detection. Because there is no detection, there is no identification. Because there is no identification, there is no avoidance. The jellyfish simply removes itself from the prey's decision-making framework. It is not evaluated as a threat because the prey's brain never registers it as an object. The fish simply swims into an empty space, and the empty space kills it. However, this terrifying efficiency is balanced by profound, almost tragic vulnerability. The exact same optical minimalism that makes the box jellyfish an invisible killer also renders it incredibly fragile. It has no armor. It has no bones. Its tissues are so delicate that they can be torn apart by the very environment it floats within. If a storm rolls in and the ocean's surface churns with turbulent waves, the box jellyfish cannot fight the current. It cannot dive deep to escape the mechanical crushing force of the water. It cannot anchor itself to a rock. It is entirely at the mercy of the physical dynamics of the sea. Its survival dictates that it must exist in a very narrow set of conditions. Currents that are strong enough to carry prey into an invisible web, but gentle enough not to shred its delicate bell. Its power is entirely conditional. It is a master of death, but it is perpetually on the brink of being destroyed by a passing wave. And yet, it would be a mistake to view the box jellyfish as nothing more than a passive, drifting trap. If you look closely at the rim of its transparent bell, you will find something deeply unsettling, something that challenges our understanding of what a primitive organism should be. Hanging from the edges of the bell are small, club-like sensory structures called rhopalia, and housed within these structures are eyes. The box jellyfish does not just have simple light-sensing patches like other jellyfish. It possesses 24 distinct eyes, grouped in clusters. Some of these are simple slit eyes, detecting basic light levels. But others are incredibly complex, complete with lenses, corneas, and retinas. They are anatomically sophisticated structures capable of forming images. But the paradox is striking. The box jellyfish has 24 complex eyes, but no centralized brain to process the visual information they gather. It is only a decentralized nerve ring, a localized web of neurons processing data on the fly. What does a creature without a brain need with such advanced vision? These eyes are constantly looking outward and upward. They allow the box jellyfish to navigate with directional intent. Unlike its purely drifting cousins, the box jellyfish can actively swim. It uses rhythmic, pulsing contractions of its bell to move through the water column, purposely steering toward areas of higher light, where plankton and small fish congregate. It uses its upper eyes to look at the surface of the water, navigating by the canopy of the mangrove forest or the shadows of the reef, actively avoiding dark, solid objects that might damage its fragile body. It occupies a haunting, intermediate space between a passive object and a conscious hunter. It does not think, not in any way we understand. It does not plot or scheme. Yet it sees, it steers. It actively positions itself in the most lethal locations possible, maximizing the mathematical probability that a fish will swim into its invisible snare. By existing in this intermediate state, the box jellyfish acts as a hidden regulator within the marine ecosystem. Because it is nearly impossible to observe naturally, its impact on the food web is consistently underestimated. It exerts a constant, silent pressure on populations of small fish and invertebrates, altering their distributions and behaviors without ever announcing its presence. It is a ghost that shapes the physical reality of the reef and the open water, its influence diffusing through the ecosystem like the very venom it injects. It forces us to rethink our definition of what a predator is. We are conditioned to fear the shark, the barracuda, the creatures with teeth and speed and forward momentum. We expect danger to arrive with a warning, a rushing shadow, a displacement of water, a tightening of muscle. The box jellyfish strips away all that theater. It proves that the most efficient weapon is not strength, and the most dangerous trait is not aggression. Its weapon is the total elimination of perception. It turns the life-giving water of the ocean into a latent hazard, a space where the line between safety and a lethal encounter simply does not exist. When you look into the blue, you see nothing. And to the box jellyfish, that is not a failure of your vision. That is a design of its perfection. It does not need to act to be dangerous. It does not need to chase to conquer. It only needs to be there, unseen and unfelt, waiting for the precise moment when the emptiness of the ocean suddenly strikes back. The foot never lands. It hangs there, suspended in the water, trapped in that final microscopic fraction of a second before contact is made. From above, everything appears perfectly normal. The seabed is a chaotic mosaic of crushed coral, dead algae, and jagged limestone. There is no movement. There is no warning. There is no subtle shift in the shadows to betray the presence of a living thing. The illusion holds with absolute, terrifying perfection. What rests on the ocean floor looks like a harmless scatter of reef debris, softened by time and the slow accumulation of ocean grit. But within that unmoving mass, a biological system lies primed. It is not waiting to hunt you. It is waiting to retaliate against your mistake. This is the stonefish. And to understand it, you must first forget everything you know about what it means to be an animal. In almost every ecosystem on Earth, life is defined by action. Survival requires movement. Predators patrol, stalk, and chase. Prey animals forage, flee, and hide. The pulse of the natural world is measured in kinetic energy. The stonefish rejects this fundamental rule entirely. It takes the concept of stillness and converts it into a weapon so absolute, so devastatingly effective, that the simple, accidental act of touching it becomes an act of predation. Only in this scenario, the roles are completely reversed. You are not hunting it. You are simply triggering its automated defense. At first glance, the body of the stonefish seems like a biological mistake. It is an exercise in geological imitation. It has abandoned the streamlined hydrodynamic curves that allow other fish to cut through the water. Instead, its skin is sculpted into a grotesque topography of irregular ridges, deep pits, and jagged outcroppings. These structures are designed to scatter the downwelling light in completely unpredictable ways, permanently breaking up any recognizable biological outline. But the disguise goes much deeper than mere shape. Covering its body are layers of dermal flaps that protrude unevenly, perfectly mimicking the torn, calcified edges of dead coral fragments. Its pigment cells do not simply paint a static color. They produce highly mottled, chaotic patterns that align with the statistical randomness of reef rubble. And the stonefish does not stop at biological mimicry. It allows the ocean to finish the disguise. Over time, microscopic algae, marine sediment, and complex biofilms are allowed to colonize its outer surface. It literally wears the living and dead texture of the reef. It does not simply resemble a rock. It becomes one, chemically, visually, and structurally integrated into the substrate. This integration is not just a neat trick. It is an exploitation of how brains work. In the shifting, dappled light of the shallow tropical waters, where constant wave action distorts shadows and millions of particles drift endlessly through the water column, vision is highly unreliable. Predators and prey alike cannot afford to carefully inspect every single inch of the seabed. It would require too much cognitive energy. Instead, they rely on rapid pattern recognition. They look for movement. They look for symmetry. They look for clear, defined outlines. Anything that does not move, anything that does not present a consistent biological signal, is immediately filtered out by the brain as harmless background noise. The stonefish exploits this perceptual shortcut. It does not actually need to be perfectly, magically invisible. It only needs to fall below the cognitive threshold of attention. It simply needs to be ignored. But beneath this masterful, static exterior lies a physiological system tuned for one of the most violent and fastest defensive responses in the marine world. Concealed along the ridge of its dorsal surface is a row of 13 rigid, hypodermic spines. These are not fins used for swimming. They are needles of hardened bone, each one sheathed in tissue and connected directly to enlarged venom glands buried deep within the muscular tissue of its back. These spines are not actively deployed. The stonefish does not rear up and strike like a snake. It does not lunge forward to stab its attacker. The entire system is entirely passive, designed to respond exclusively to external mechanical force. It is a living landmine. When pressure is applied from above, when a predator attempts to take a bite, or when a human foot steps down, the tissue covering the spine is pushed back. The hardened needle easily pierces the flesh of the intruder. But more importantly, the downward pressure of the attack mechanically compresses the venom glands at the base. This physical squeezing forces the venom up through hollow channels running the length of the spine, injecting the toxic payload deep into the wound. The delivery is entirely mechanical, not behavioral. The stonefish does not make a conscious decision to sting you. You sting yourself. The environment decides when the weapon is fired, and the weapon itself is a marvel of biochemical warfare. The venom of the stonefish is an incredibly complex, highly unstable cocktail of proteins and peptides designed to completely dismantle multiple physiological systems simultaneously. It does not just cause pain, it redefines it. The toxins immediately attack the ion channels in the victim's nerve cells, forcing them to fire wildly, sending cascading waves of absolute, agonizing pain to the nervous system. The intensity of this pain is often described as mind-shattering, capable of inducing shock and delirium within minutes. But the venom is also myotoxic and cardiotoxic. It begins to break down muscle tissue, leading to severe, uncontrollable spasms, and in many cases, total paralysis of the affected limb. As the toxins enter the bloodstream, they travel to the heart, altering the electrical rhythm of the cardiovascular system. Blood pressure plummets. Arrhythmia sets in. In severe, untreated cases, this cardiovascular collapse leads directly to death. In pure ecological terms, this is massive overkill. A predator attempting to eat a stonefish does not just learn a lesson, it is utterly destroyed. But why? Why does an animal need such a catastrophically powerful defense system? The stonefish is universally feared, often framed as a dominant monster of the shallows, a creature sitting confidently at the top of the defensive hierarchy. But this framing is completely wrong. The stonefish is not a dominant apex predator. In many ways, it is profoundly, tragically vulnerable. Look closely at its body. It lacks a streamlined shape. It lacks powerful swimming muscles. It lacks agility. If it is discovered, if its camouflage fails, it cannot outswim a shark. It cannot dart away into a crevice like an eel. It is too slow, too bulky, too cumbersome. Its entire strategy for existence is built on the absolute necessity of not being noticed. The venom is not a tool of conquest. It is a last line of defense. It is an extreme, desperate failsafe for when invisibility breaks down. This is the first great narrative reversal of the stonefish. The most potent lethal weapon in its entire arsenal exists precisely because the animal is physically weak. Its apparent dominance is rooted directly in an underlying evolutionary constraint. The horrific venom compensates for its immobility. The hypodermic spines compensate for its total inability to flee. What we perceive as terrifying strength is, in biological reality, a highly specialized response to profound vulnerability. And this immobility dictates not just how it defends itself, but how it feeds. While its defensive capabilities are legendary, the stonefish is fundamentally an ambush predator. Its diet consists of small fish, shrimp, and crustaceans that wander too close. And here again, we see stillness converted into an offensive tool. Prey animals moving through the reef are deeply conditioned to ignore static, textured objects. A rock does not pose a threat. A patch of algae does not give chase. The stonefish leverages this deeply ingrained assumption, remaining perfectly, breathlessly motionless for days at a time, waiting for a target to drift into an incredibly narrow strike zone. It does not stalk. It does not chase. It simply waits for the mathematics of probability to bring a meal to its mouth. When a fish finally drifts within inches of its face, the transition from inert rock to violent predator is so sudden it defies belief. In a burst of kinetic energy that lasts only a few milliseconds, the stonefish drops its lower jaw and flares its gills. The sudden, massive expansion of its buccal cavity creates a violent drop in pressure. It literally creates a vacuum in the water. The surrounding water and the prey suspended within it are instantly sucked inward. The strike is so blindingly fast that it bypasses the prey's nervous system entirely. There is no time to register the movement, no time to trigger a flight response. The prey is hovering safely over a rock in one frame of reality, and in the next, it is already trapped inside a crushing jaw. This dual role, simultaneously functioning as a passive, lethal defensive mind and a hyper-fast, active ambush predator, positions a stonefish at a wholly unique intersection of evolutionary strategies. It collapses the distinction between the environment and the organism. When it hunts, the reef is not just a backdrop. It is a functional extension of the stonefish's own body. But this masterful strategy carries a heavy, unavoidable burden. The effectiveness of the stonefish depends entirely on the broader dynamics of the ecosystem around it. Coral reefs are environments of intense visual complexity. They are defined by high biodiversity, chaotic structures, and sensory overlap. In such a system, sensory overload is a default state. Visual signals constantly overlap. Chemical cues diffuse in the currents, and movement is happening everywhere. It is precisely under these chaotic conditions that organisms evolve to filter out background noise. The stonefish relies on this chaos. It needs the visual clutter to become the ignored object. But the reef is not a static painting. It is a living, shifting environment subject to profound disturbances. When water temperatures rise and coral bleaches and dies, the vibrant, chaotic background fades to a stark, uniform white. When severe storms break apart the complex architecture of the reef, turning it into flat, sandy plains. When pollution causes massive, suffocating algae blooms that smother the rocks, the visual landscape changes dramatically. The stonefish, heavily modified to mimic a specific type of complex rubble, suddenly finds itself exposed. It cannot quickly change its skin like an octopus. It cannot swim away to find a better hiding spot. It must continuously hope that its physical form matches the degrading environment around it. Its success and its very survival is therefore inextricably tied to the health, complexity, and structural diversity of the reef itself. A degraded, dying reef offers no cover. In a barren landscape, a rock with eyes becomes painfully obvious. This leads to a second narrative reversal. The stonefish is almost always perceived as an isolated, self-sufficient killer, a solitary monster waiting in the dark. But in reality, It is completely dependent on a vast network of ecological processes that maintain the very patterns it relies on to hide. Its invisibility is not solely its own creation. It is co-produced by the living reef. If the reef dies, the stonefish loses its cloak, and its evolutionary masterpiece becomes a death sentence. There is also a fascinating temporal dimension to the life of a stonefish. It does not experience time the way active predators do. A shark must constantly move, constantly seek, constantly burn energy. The stonefish is free from the tyranny of continuous motion. It can afford to wait. It can endure incredibly long periods of absolute inactivity. Its metabolism slowed to a crawl, conserving energy while waiting for the perfect alignment of conditions. This aligns perfectly with constraints of a purer ambush predator. The energy gained from a single, successful suction strike can offset weeks of fasting. The ultimate trade-off of this lifestyle is infinite patience. The life of a stonefish is measured not in continuous flow of motion, but in violently punctuated events. Weeks of silent, invisible waiting shattered by milliseconds of explosive action, followed by weeks of silence once again. But for the organisms that encounter it, whether a small fish seeking shelter or a human foot seeking purchase, time behaves very differently. For them, time collapses entirely. The transition from absolute safety to catastrophic danger is instantaneous. A misplaced footstep, a misjudged shadow, a lapse in concentration. These do not result in a gradual escalation of threat. There is no warning growl, no display of bright warning colors, no posturing. There is only a binary outcome. You are safe or you are severely injured. You are alive or you are caught. The stonefish enforces this brutal binary through its very design. The cost of detecting it is that it is already too late. In the end, the stonefish represents a fundamental challenge to how we perceive the natural world. It exposes the fragile limits of our visual processing, laying bare the dangerous assumptions we make about our environment. We assume that danger announces itself. We assume that stillness equals safety. But the most unsettling realization about the stonefish is not the excruciating potency of its venom, nor the invisible, vacuum-force precision of its ambush. It is a philosophical horror. It is a realization that the stonefish does not need to act in order to be dangerous. It does not need to harbor malice or hunger or intent. It does not need to hunt you. It only needs to be there. And in its absolute stillness, it proves that the environment itself can hold a loaded gun. The reef is a landscape defined by panic. Survival here is a constant, frantic mathematics of speed and distance. Prey animals survive by recognizing the signs of impending attack, the sudden twitch of muscle, the tightening of a silhouette, the violent displacement of water. When danger approaches, the rules are simple. You identify the threat, you calculate the trajectory, and you flee. But what do you do when the danger does not chase you? What do you do when the predator simply drifts into your space and slowly, beautifully unfurls? A small fish hovers near a coral outcropping. It is hyperaware, its nervous system wired to detect the high-speed strike of a grouper or the sudden lunge of an eel. But the shape drifting toward it does not trigger these alarms. It is not moving with aggressive intent. It is expanding. A wall of delicate, impossibly long spines and feather-like membranes opens in slow motion, drifting outward like the petals of a strange, blooming flower. It seems too fragile to be a threat. It looks ornamental, a piece of drifting art rather than an advancing killer. And in that moment of hesitation, the geometry of the ocean completely changes. What was once open water suddenly becomes a corridor. What were once infinite escape routes violently collapse into a narrowing funnel. The small fish does not swim away. It is not trapped by physical force, nor is it restrained by a net. It is trapped because the psychological rules of space around have just been rewritten. At the center of this expanding architecture hovers the lionfish. It is motionless, save for the hypnotic, rippling adjustments of its fins. Its body is draped in bold, violent stripes of red, brown, and stark white. In a world where camouflage is the ultimate currency of survival, the lionfish commits the ultimate heresy. It refuses to hide. It does not blend into the coral. It does not mimic the shadows. It is a beacon of contrast, deliberately designed to be the most conspicuous object in the water. This challenges a fundamental assumption we hold about the natural world. that to be a successful hunter, you must be invisible or you must be overwhelmingly fast. The lionfish is neither. It moves with lethargic, almost arrogant grace. Yet, this extreme visibility is not a vulnerability. It is the core of its weapon. The lionfish does not hide from the visual field of its prey. It overloads it. To understand how it hunts, you must understand how a prey fish sees the world. Small reef fish rely on mental shortcuts to survive. They scan for recognized silhouettes. A shark looks like a shark. An eel looks like an eel. The lionfish, however, destroys its own silhouette by extending its massive pectoral fins and raising its crown of dorsal spines. It shatters its own outline. The prey does not see a fish. It sees a shifting, ambiguous, chaotic structure. More importantly, this structure perfectly masks the location of the lionfish's mouth. The focal point of the danger is completely hidden behind a curtain of distraction. But the true genius of the lionfish lies in how it uses these fins. When it initiates a hunt, it does not rely on a burst of speed. It relies on spatial manipulation. It spreads its pectoral fins wide, creating a massive, semicircular wall. These fins are not used to grab or hold the prey. They are used as visual boundaries. Fish are instinctively terrified of crossing unknown, irregular barriers. When the lionfish slowly advances with its fins spread, the prey's brain perceives a closing wall. The fish's natural instinct is to back away, seeking open water. But the lionfish is anticipating this. By subtly adjusting the angle of its fins, it gently steers the prey, blocking off the left, blocking off the right, closing invisible walls. The predator is not chasing. It is orchestrating. It is playing a game of chess where the prey is forced to move exactly where the predator wants it. And the only open path left, the only apparent route of escape the prey can see, leads directly to the center of the lionfish's face. The prey effectively corners itself. This requires an astonishing level of neurological coordination. The lionfish is not just reacting to a moving target. It is continuously mapping the three-dimensional space, predicting the prey's escape vectors, and adjusting its own dynamic structure to cut those vectors off. By the time the actual strike happens, the prey's options have been mathematically reduced to zero. The strike itself is not the explosive, vacuum-inducing suction of frogfish, nor is it the high-speed pursuit of a shark. It is simply the inevitable conclusion of the trap. A sudden, short forward thrust, a snap of the jaws, and the prey is gone. Yet, there's an even deeper, more insidious layer to this hunt, one that occurs entirely outside the realm of vision. Fish possess an organ known as the lateral line, a highly sensitive network of mechanoreceptors running down the sides of their bodies. This lateral line detects minute changes in water pressure and current. It allows a fish to feel a predator approaching in the dark or sense the movement of the water being pushed ahead of an attacker. It is a near-flawless early warning system. The lionfish knows how to hack this system. As it slowly corrals its prey, studies suggest the lionfish engages in a form of physical jamming. It shoots rapid, directed jets of water out of its mouth toward the prey. These subtle pulses of water hit the prey's lateral line, flooding its mechanosensory system with chaotic noise. It is the biological equivalent of throwing a flashbang. The prey is suddenly blinded not just visually by the confusing fins, but sensorially. It cannot feel the water correctly. It cannot judge the distance of the approaching predator. Deafened and confused by this invisible acoustic weapon, the prey simply freezes. But how does a fish that moves this slowly and stands out this clearly survive in an ocean filled with larger, faster predators? Why doesn't a passing shark simply tear out the water column? The answer lies in the crown of thorns it wears upon its back. Along its dorsal, pelvic, and anal fins are 18 needle-sharp spines. These are not used for hunting. They are defensive weapons, and they are absolute. Each spine is deeply grooved and sheathed in glandular tissue that produces a highly complex, excruciatingly painful venom. When a predator makes a mistake of attempting to bite a lionfish, the pressure strips back the tissue, and the needles drive deep into the attacker's flesh, delivering the toxin directly into the bloodstream. This venom is a nightmare of neurotoxins and cytotoxins. It induces immediate, mind-numbing localized pain, followed by tissue necrosis, extreme swelling, and in smaller predators, systemic paralysis and cardiovascular failure. Because of this devastating defensive capability, the lionfish's bright, highly visible stripes are revealed to be something else entirely: aposematism, a biological warning sign. It is not trying to blend in because it wants every creature in the ocean to know exactly what it is. The stripes scream a simple message: I am not hiding because I am untouchable. Predators learn very quickly that the beautiful, slow-moving fish is a vessel of agony, and so they leave it alone. They swim past it. They ignore it. This creates a profound narrative reversal. By being overwhelmingly visible and heavily armed, the lionfish buys itself immunity, and this immunity gives it a terrifying advantage. Because it does not have to constantly look over its shoulder, because it does not have to expend massive amounts of metabolic energy fleeing from larger predators, it can dedicate almost all of its energy to one single task: consumption. It moves slowly, conserving its calories. It hunts with extreme, calculated efficiency. It lives a life virtually devoid of fear. This unique combination, the perfect energy-efficient hunting strategy, combined with total immunity from predation, turns a lionfish into a localized ecological disaster when it is removed from its native habitat. In areas where it has been introduced, like the Caribbean and the Atlantic, it encounters naive ecosystems. The local prey fish have not evolved to understand the visual deception of the lionfish's fins. They do not recognize the expanding wall as a threat until it is too late. And the local predators do not know how to bypass its venomous spines. The result is a slaughter. A single lionfish can decimate the juvenile fish population of a reef in a matter of weeks. They are gluttons, expanding their stomachs to accommodate massive amounts of prey, altering the structure of the entire food web. Without the natural checks and balances of their home waters, their elegance masks a ruthless, unstoppable efficiency. They are not just surviving, they are conquering. However, this perfection is not without its limitations. The lionfish's strategy is heavily dependent on the architecture of the reef. It needs the coral walls, the outcroppings, the tight spaces. It uses the complex topography of the reef as an anvil against which to hammer its prey. It backs them into corners, using the natural rock to close off the final escape routes. If you take a lionfish and place it in the vast, featureless expanse of the open ocean, its primary weapon is neutralized. Without physical boundaries to assist its visual corralling, its slow speed becomes a fatal flaw. The prey can simply swim around expanding fins. Its power is contextual. It requires a labyrinth of the reef to turn its slow-motion dance into a lethal trap. In the end, the lionfish forces us to redefine the concept of a predator. We are conditioned to associate lethality with aggression. With the sudden snap of a jaw, the explosive burst of muscle, the shadow dropping from above, we expect predators to overpower their victims. The lionfish overpowers nothing. It manipulates. It changes the context in which the prey makes decisions, feeding them false spatial data, jamming their sensory organs, and gently guiding them into a box of their own making. Its beauty is not an accident of nature. It is a highly functional, deeply deceptive mechanism. The flowing fins, the stark warning colors, the slow, arrogant drift, they are all cogs of a machine designed to mislead. It proves that sometimes the most effective way to be a ghost is to stand in the light, show the world exactly who you are, and let them misunderstand you until the very last second. The sand does not move until it decides to become a snake. You are looking at the shallow, sunlit floor of a tropical estuary. It is an exposed, unforgiving landscape. There are no dense coral labyrinths here, no deep crevices to disappear into. It is a shifting mosaic of barren sand flats, broken shells, and sparse, silted currents. For a soft-bodied animal, this environment is a death sentence. In the open, visibility is absolute, and vulnerability is a guarantee. Suddenly, a creature slides across the seafloor. Its body is composed of stark, alternating bands of black and white. It moves with a rigid, undulating posture, a deliberate and menacing glide that commands the space around it. To the nervous system of any predator watching, every single visual signal screams danger. This is the banded sea kite, one of the most venomous marine reptiles on the planet. Its bite delivers a neurotoxin so potent that an attack is universally recognized as fatal. Small fish violently scatter before it. Even experienced, heavy-bodied predators hesitate, instantly calculating the risk and choosing to withdraw. But beneath this terrifying illusion, there are no scales. There are no fangs. There are no venom glands. There's only a soft, boneless mass of muscle and a deeply distributed, hyperelastic mind that is rewriting reality in real time. This is the mimic octopus, and it does not survive by hiding from the ocean. It survives by convincing the ocean to fundamentally misidentify it. To comprehend the sheer magnitude of this deception, we must first abandon our traditional understanding of camouflage. When most animals attempt to conceal themselves, they engage in background matching. A flounder mimics the color of the sand. A moth mimics the bark of a tree. They ask the environment to absorb them. They attempt to reduce their signal to zero. The mimic octopus operates on a completely different, almost psychological plane of warfare. It does not aim to disappear into the background. It actively constructs a false, highly conspicuous foreground. It is not asking, "Can I avoid being seen?" It is asking the predator, "What do you fear the most right now?" And then it becomes that fear. The physical mechanics that make this possible begin at the microscopic level of the skin, utilizing the same complex technology found in other cephalopods. Millions of chromatophores, iridophores, and leucophores expand and contract under direct, instantaneous neural control. In fractions of a second, the octopus can completely repaint its entire body. But color alone is not enough to fool an ecosystem built on millions of years of pattern recognition. An octopus painted like a sea snake, but shaped like an octopus, is just a highly visible meal. The mimic octopus must alter its physical architecture. It must become a shapeshifter. When a threat approaches, the octopus makes a split-second evaluation of the predator and selects a specific nightmare from its repertoire. If a predatory fish swims overhead, the octopus does not flee. Instead, it collapses its body entirely. It flattens its soft mantle against the sand, pulls its 8 arms together, and begins to ripple its edges. It changes its color to a mottled, sandy brown, adopting the exact swimming motion of a toxic flatfish. It glides just above the substrate, its movement a perfect mechanical replica of an animal that predators know is heavily armored and difficult to consume. If the threat is more aggressive, the octopus escalates the illusion. It pulls 6 of its arms tightly into the burrow of the sand, leaving only 2 exposed. It aligns them perfectly, altering its pigments to the stark black and white bands of the sea snake. It then moves those 2 arms in opposite directions, creating the undulating, serpentine crawl of the venomous reptile. It is a performance of pure confidence, exploiting the evolutionary memory of predators that have learned over countless generations that striking such a creature means instant death. But perhaps its most audacious performance is its imitation of the lionfish. When caught entirely in the open water column, with no sand to bury itself in, the octopus flares outward. It spreads its 8 arms wide, letting them trail through the water like the long, venomous spines of the lionfish. It adopts the stark, warning stripes of aposematic coloration. It hovers, moving with the same lethargic, arrogant drift of the untouchable predator. This is not passive camouflage. It is active, highly calculated impersonation. It is a behavioral strategy rooted in the direct manipulation of predator cognition. The nervous system that enables this theatrical masterpiece is unlike that of almost any other animal on Earth. Rather than centralizing all control within a single, primary brain enclosed in a skull, the octopus distributes its mind throughout its entire body. A massive portion of its neurons are located within its 8 arms. Each arm contains dense, highly complex neural networks capable of semi-autonomous action, processing, and decision-making. This profound decentralization allows for a level of multitasking that borders on the supernatural. While one arm is probing the substrate for the subtle chemical signature of a hidden crab, another arm is independently adjusting its posture to maintain the curvature of a fake sea snake. While the mantle subtly shifts its coloration to match the angle of the incoming sunlight, the animal is simultaneously monitoring the exact distance and trajectory of the predator above. It is not performing a single trick. It is running multiple, parallel biological processes simultaneously, each one perfectly calibrated to reinforce a single, desperate outcome: hesitation. Hesitation in the ocean is everything. Predation operates on incredibly strict, Unforgiving thresholds. A hunt is a split-second cost-benefit analysis driven by visual cues, movement patterns, and risk assessment. A predator that misidentifies its prey risks injury, venom exposure, or a catastrophic waste of metabolic energy. The mimic octopus violently exploits this mathematical calculation. By presenting itself as something actively dangerous, it forces the predator into an immediate dilemma: attack and risk fatal error, or withdraw and lose a meal. The predator's brain stalls. It tries to reconcile the visual data of a highly venomous creature with the spatial context of the encounter. And in that crucial, stretching moment of cognitive indecision, the octopus escapes. Its survival is not based on outswimming danger. It is based on hacking the decision-making software of its enemies. Yet, this strategy carries its own terrifying risks. To impersonate a venomous species is to adopt its visibility. The lionfish is not invisible. It is wildly conspicuous, its elaborate fins broadcasting a continuous warning. The sea snake does not hide. It moves with deliberate, highly visible confidence. By choosing to mimic these specific animals, the octopus willingly abandons the safety of the shadows. It forces itself into the spotlight. It intentionally enters a perceptual field of predators that might otherwise have completely ignored it had it simply looked like a rock. Because of this, the deception must be absolutely flawless. It must be convincing enough to immediately cross the predator's risk threshold. A flawed imitation, a sea snake that moves just a fraction too stiffly, a lionfish whose colors are slightly dull, could invite exactly the attack it is trying to avoid. Here, the mimic octopus reveals profound philosophical reversal of survival. Invisibility is not always the safest strategy. Sometimes the most effective way to avoid being eaten is to make sure you are seen as clearly as possible, but as something else entirely. But the mimic octopus is not solely a defensive illusionist. When it shifts its focus from survival to starvation, it reverses its own strategy. Instead of appearing dangerous to deter predators, it adopts forms that lower the guard of its prey. As it hunts across the barren sand flats, it may flatten itself perfectly against the substrate, becoming nothing more than a harmless, shifting patch of sand. Or it may curl its arms chaotically, letting the current push it along the bottom, perfectly mimicking a drifting piece of dead algae or coconut shell. Small crustaceans, worms, and gobies watch this debris drift past. They interpret these shapes as part of the non-threatening, inanimate environment. They relax, they ignore it, and then, without a single warning signal, the illusion violently collapses. The drifting debris erupts. Arms surge forward with terrifying speed, the webbing between them expanding like a parachute, trapping the prey against the sand. Suction cups lock onto the target, and it is instantly drawn inward toward a crushing, razor-sharp beak. The exact same physiological system that deters predators is weaponized to become a tool for ambush. But even in the hunt, the logic is infinitely more complex than a simple disguise. The octopus is not merely hiding from its prey. It is, once again, manipulating sensory biases. Many small marine organisms rely almost entirely on motion detection and high-contrast edges rather than detailed, high-resolution visual recognition. By intentionally minimizing sudden, jerky movements and maintaining low-contrast, muted patterns, the octopus effectively erases itself from the perceptual filters of its targets. It does not need to be invisible in the physical sense. It only needs to fall below the cognitive detection threshold. This reveals a deeper, universal biological principle. Perception is not a perfect mirror of reality. It is a highly filtered, deeply flawed interpretation shaped by millions of years of evolutionary pressures and shortcuts. The mimic octopus does not actually change the physical world around it. It changes how that world is perceived. Its ultimate weapon is invisibility within the cognitive frameworks of other species. However, the ocean is not a static environment, and neither are its inhabitants. Predators learn. They adapt. A large predatory fish that survives an encounter with a mimic octopus, or watches one from a distance, may begin to recognize the subtle, underlying inconsistencies in the disguise. It might notice the way the sea snake arms articulate just a little too fluidly. It might register the timing of its movements or a slight, microscopic mismatch in the stripe pattern. Over time, the effectiveness of a given impersonation may decline within a specific local ecosystem. When this happens, the octopus cannot rely on instinct alone. It must refine its repertoire. It must adjust its performance, select new models to impersonate, and consciously evolve its deception. This ongoing, high-stakes arms race introduces a second narrative reversal. The mimic octopus is not a fixed, genetic master of disguise. It is an active, improvising participant in a dynamic evolutionary feedback loop. Its success depends not on a single, perfected strategy hardwired into its DNA, but on its fluid ability to stay one step ahead of the perceptual adaptations of both its predators and its prey. It is, in essence, a jazz musician in a system that brutally punishes predictability. The cost of this extreme flexibility is energy. Maintaining rapid color changes, holding complex, unnatural postures, and continuously assessing the environmental threat level requires massive, draining metabolic resources. The octopus cannot sustain this high-level, active mimicry indefinitely. There are inevitable moments when it must retreat, reduce its activity, and conserve energy, reverting to simpler, less demanding forms of background camouflage. The weapon, therefore, is not a permanent shield. It is deployed highly selectively, strictly in response to specific, evaluated threats. And this selective use underscores the staggering intelligence of the animal. The mimic octopus does not just randomly cycle through its disguises in a panic. It chooses them. Observation of these creatures in the wild suggests that they deliberately tailor their impersonation to the specific type of predator they encounter. If confronted by a damselfish, which is highly territorial and aggressive, the octopus will mimic a sea snake, a known predator of damselfish. It selects the exact form that is mathematically most likely to trigger avoidance in that specific observer. This implies a level of environmental awareness, memory, and decision-making that goes far beyond simple biological reflex. It suggests that the octopus is not just reacting to a stimulus. It is evaluating the identity of its enemy, accessing a mental library of fears, and executing the appropriate psychological countermeasure. In the end, the mimic octopus does not dominate its barren, exposed environment through physical strength. It has no armor. It has no venom. It has no blinding speed. It survives entirely by rewriting the rules of engagement. In a world where being seen almost always means being eaten, it transforms visibility into an impenetrable shield. It turns recognition into fatal misrecognition. It weaponizes the assumptions, the shortcuts, and the expectations of every other mind in the water. And in doing so, it exposes a final, profoundly unsettling truth about life in the ocean. The greatest danger is not always the monster lurking in the dark, the thing you cannot see. Sometimes, the greatest danger is the thing resting in the bright, clear light of day, the thing you are looking right at, the thing you are absolutely certain you understand. The water parts without a single fraction of urgency, and that is precisely where the danger lies. When we imagine the arrival of a predator in the open ocean, we are conditioned to expect a disruption, a sudden violent acceleration, a tightening arc of pursuit, the chaotic thrashing of a struggle, or the rushing shadow of something massive displacing the water. We expect the ocean to react, to signal the presence of a killer through frantic scattering of bait balls or the sudden silence of the reef. But as you watch this creature glide to the blue column, there is no disruption. There is no burst of kinetic force. A long, ribbon body moves forward with rhythm so measured, so perfectly calibrated, that it seems entirely indifferent to the life buzzing around it. Small fish do not scatter in a panic. They merely adjust their position slightly, drifting aside just as they would for a piece of floating driftwood, a passing shadow, or a shifting current. Nothing about the movement suggests a threat. There is no coiled tension preparing to strike. There is no hyper-focused gaze tracking a target. And yet, housed within this calm, undulating trajectory is one of the most chemically concentrated, lethal weapons in the entirety of the marine world. This is a sea snake. And its invisibility is not built on hiding in the shadows. It is built on a complete, terrifying absence of urgency. To understand the genius of the sea snake, you must first understand the brutal reality of its environment. Unlike the ambushed predators that sink into the complex architecture of the coral reef, dissolving into the substrate, the sea snake spends vast amounts of its time in the open water. This is a domain where physical concealment is a mathematical impossibility. There are no fixed surfaces to merge with, no jagged coral structures to mimic, no shadows to retreat into. In the pelagic zone, visibility is absolute and unavoidable. If an animal is moving through the space, it will be seen. The challenge, therefore, is not to disappear visually. The challenge is to disappear behaviorally. It is to move in a way that fundamentally fails to trigger the neurological alarms of every other organism in the water. The sea snake achieves this through a masterpiece of evolutionary engineering known as kinematic camouflage. It does not blend into the background. It blends into the background motion of the ocean itself. Look closely at its anatomy. Its body is laterally compressed, flattened side to side, terminating in a paddle-like tail. This shape does not allow for the explosive, high-speed bursts of velocity that a shark or a barracuda uses to run down prey. Instead, it is optimized for sustained, hyper-efficient, continuous motion. It propels itself through slow, undulating waves of muscle contraction that travel seamlessly from the back of its head down to the tip of its tail. The result is a glide that appears entirely effortless. It lacks the abrupt, jerky changes in velocity or the sharp, aggressive directional shifts that define the predatory chase. And this is the key to its invisibility. The sensory systems of small reef fish and pelagic prey are highly tuned instruments, but they are subject to strict metabolic limits. In an ocean filled with constant movement, drifting algae, rolling waves, shifting tides, a small fish cannot afford to treat every single moving object as a mortal threat. If it panicked at every passing shadow, it would burn through its energy reserves and starve in a day. To survive, the fish's brain must filter the noise. It prioritizes specific signals: rapid acceleration, high contrast silhouettes rushing inward, erratic thrashing. The sea snake's perfectly fluid motion falls entirely outside this threat parameter. To the lateral line and the visual cortex of a nearby fish, the snake registers as low-priority movement. It is categorized not as an active hunting predator, but as part of the ambient, non-threatening flow of the environment. The fish sees the snake, but its brain does not classify it as dangerous. The sea snake exists perfectly within a perceptual blind spot created by the prey's desperate need for sensory efficiency. It is seen, but it is fundamentally unrecognized. Yet, beneath this hypnotic, calming exterior lies a predatory system that operates with surgical precision rather than brute speed. As the sea snake transitions from the open water down to the complex architecture of the reef, its hunting strategy shifts. Its head is remarkably small relative to the length and girth of its body. This is not an anatomical flaw. It is a highly specialized key designed to unlock the reef's most secure vaults. When small fish and crustaceans feel threatened, their instinct is to abandon the open water and wedge themselves into the deepest, narrowest crevices of the coral matrix. Against a shark or a grouper, this strategy is flawless, but the sea snake turns this sanctuary into a tomb. It effortlessly slides its narrow head and elongated body into these confined, labyrinthian spaces. Inside the rock, the spatial dynamics completely invert. The prey can no longer rely on its speed or maneuverability. It is backed into a corner, trapped in a narrow tunnel where the sea snake's fluid, flexible form becomes an insurmountable advantage. When the strike finally comes, it is a brief, almost clinical departure from the snake's otherwise steady motion. It does not explode forward in a violent blur. It does not thrash to subdue its target. It simply positions its small head within striking distance and delivers a bite that is so subtle, so controlled, it is sometimes barely perceptible amidst the gentle sway of the water. The snake does not need to rely on mechanical force to hold the struggling prey. It does not need powerful, crushing jaws. The effectiveness of the strike relies entirely on the payload delivered in that fraction of a second. The venom of the sea snake is among the most toxic substances in the natural world. It is a highly refined, complex mixture of neurotoxins designed to completely sever the communication pathways between the prey's nervous system and its muscles. These toxins flood the bloodstream and instantly bind to the receptors at the neuromuscular junctions. They act as biological roadblocks, preventing the brain's electrical signals from ever reaching the muscle tissue. The result is a rapid, progressive, and inescapable paralysis. It begins at the site of the bite, freezing the muscles nearest the wound, and rapidly cascades through the entire body, eventually reaching the respiratory system. For a small fish trapped in a coral crevice, this biochemical shutdown occurs in a matter of moments. It is completely immobilized before it can even attempt to thrash its way to freedom. This terrifying biochemical efficiency is what allows the sea snake to maintain its incredibly low-energy hunting strategy. It does not need to waste precious calories wrestling with a desperate fighting animal. It does not need to tear its prey apart. A single, perfectly placed bite is all that is required. The snake simply bites, waits a few moments for the venom to rewrite the prey's physiology, and then consumes the incapacitated meal whole. This reveals a profound narrative reversal of the sea snake. Its slow, calming movement, which we initially perceived as a physical limitation or a form of passive concealment, is actually the anchor of a highly integrated, masterfully orchestrated strategy. Its apparent lack of aggression is a calculated mechanism. By moving in a way that avoids triggering the panic responses of its prey, it completely eliminates the need for speed. Its physical weakness, the absolute inability to engage in a high-speed pursuit, is transformed into its greatest strength through the evolution of a venom that compensates for the lack of kinetic energy. The sea snake does not need to be fast, because it operates in a system where speed is no longer the primary determinant of success. The strike is not the beginning of the hunt. The strike is merely the inevitable conclusion of a process that began the moment the prey's brain looked at the snake and decided not to react. But this mastery of the ocean comes with severe, unbreakable tether to the world above. Despite its perfect adaptation to marine environment, the sea snake is still a reptile. It does not possess gills. It cannot extract all the oxygen it needs from the water. No matter how deep it dives, no matter how successfully it navigates the reef, there is an invisible clock counting down in its blood. Eventually, it must return to the surface to breathe air. This physiological requirement introduces a massive vulnerability into its otherwise flawless existence. The transition from the depth to the surface is the most dangerous journey a marine reptile can make. As it leaves the cover of the reef and ascends through the water column, it is exposed against the light. At the surface, its movement is constrained, its options for escape are eliminated, and it becomes highly visible to a completely different set of predators. Sea eagles sweeping down from the sky, and large pelagic sharks attacking from below. To mitigate this fatal exposure, the sea snake has evolved a staggering physiological workaround. It has developed cutaneous respiration. It can literally breathe through its skin. A significant network of capillaries runs just beneath the surface of its scales, allowing the snake to absorb dissolved oxygen directly from surrounding seawater and diffuse carbon dioxide back out. In some species, this skin breathing can account for up to 30% of their total oxygen requirement. This adaptation dramatically extends the duration of their dives, reducing the frequency with which they must expose themselves at the perilous boundary between water and air. It is another brilliant negotiation between visibility and function, allowing the animal to stay submerged in its realm of slow-motion execution for as long as biologically possible. In the grand architecture of the marine ecosystem, the sea snake represents a form of predation that defies our deepest instincts about danger. It proves that a threat does not need to be loud or fast or aggressive to be absolute. It moves through the environment not by conquering it with force, but by integrating with its fundamental rhythm. It becomes part of the background motion, flowing with the current rather than fighting against it. Its weapon is not hidden in the sense that it cannot be seen. It is hidden in the sense that it is simply unrecognized. And in the end, the most unsettling realization about the sea snake is not the lethal potency of its venom, nor the clinical precision of its tiny jaws. It is the way it weaponizes tranquility. In a world where we expect danger to reveal itself through panic, urgency, and chaos, the sea snake does the exact opposite. It remains perfectly, chillingly steady. And in that steadiness, right in front of your eyes, it completely disappears. The water folds inward before the prey can even register the existence of danger. There is no visible attacker dropping from above. There is no dark shadow accelerating from a distance. There is no tightening art of pursuit, no displacement of water to warn the lateral line of an approaching threat. A small, brightly colored reef fish hovers casually over what appears to be a lifeless, decaying patch of the ocean floor. It is an uneven, chaotic cluster of sponge-like growth, mottled in dull oranges and browns, blending seamlessly into the jagged geometry of coral rubble and settling sediment. The fish drifts closer, its eyes scanning the open water for familiar shapes of predators. It finds nothing, and then, without any transition, the physical space where the fish exists simply collapses. The water itself seems to violently inhale. In less time than it takes for a neural signal to travel from a fish's eye to its brain, the prey is no longer there. The environment has completely consumed it. Only in a quiet aftermath does the perfect illusion fracture, revealing that the lump of decaying reef was never static. It was never a rock. It was a massive hinge mouth waiting in the dark. This is a frogfish, and it does not hunt by movement. It hunts by becoming the absolute, terrifying absence of movement, erasing its own presence so completely that the prey forgets the very concept of danger. At the core of the frogfish's strategy is a radical, almost blasphemous redefinition of what it means to be a predator. In the high-stakes arena of marine ecosystems, predation is almost universally a contest of kinetics. It is a biological arms race of speed, endurance, and hydrodynamic coordination. Sharks develop torpedo-like bodies to cut through the water. Barracudas evolve explosive fast-twitch muscles. Dolphins utilize hyper-coordinated pack hunting. The frogfish abandons all of these evolutionary investments. It throws away the rulebook of kinetic survival. Look at its body. It is grotesque, lumpy, and entirely devoid of the sleek, streamlined curves that define aquatic efficiency. Its fins have been heavily modified by evolution, no longer used for graceful swimming, but transformed into bizarre, jointed, limb-like appendages. The frogfish does not swim through its kingdom. It slowly, awkwardly walks across the substrate. Its musculature is not built for sustained, energy-burning motion, but for highly localized, explosive, instantaneous force. In the grand ledger of evolutionary trade-offs, the frogfish has made a staggering exchange. It has completely sacrificed mobility for absolute precision. It has traded the ability to chase the ability to erase the need for a chase entirely. This extreme trade-off is made possible by what is arguably the most immersive and absolute form of camouflage in the ocean. The skin of a frogfish is not just colored to match its surroundings. It is a living, three-dimensional topography. It is covered in fleshy protrusions, dermal appendages, and irregular textures that perfectly mimic the swaying fronds of dead algae, the porous, pitted surfaces of tube sponges, or the broken, calcified edges of dead coral. Pigment cells distribute color across its body in wildly unpredictable, asymmetrical patterns. It does not try to match a single, uniform background, but rather the statistical randomness and visual clutter of reef debris. The mimicry is so profound that many species of frogfish actually host living microbial gardens and marine algae directly on their skin, further integrating their biology into the living fabric of their surroundings. The result is not merely concealment. It is total assimilation. The frogfish does not sit on the reef. It becomes a structural unit within it. This level of assimilation brutally exploits a fundamental principle of sensory neurology. For a small fish navigating the highly complex, overwhelming environment of a coral reef, the brain is constantly flooded with data. To prevent cognitive overload, the fish's nervous system must filter this environment, prioritizing visual and physical signals that are historically associated with danger, sudden movement, sharp contrast, and anomalous shapes. Static, highly irregular, heavily textured objects are immediately categorized by the brain as background architecture. They are sorted into the mental spam folder and ignored. The frogfish parks itself precisely within this category. It is not that the prey cannot physically see the shape of the frogfish. It is that the prey's brain refuses to process the shape as a biological entity. The frogfish exists outside the perceptual algorithms that govern the prey's survival. Yet, if the frogfish were merely an invisible rock, it would starve. Waiting passively for a fish to accidentally swim directly into its mouth is a game of terrible mathematical odds. And this is where the genius of the frogfish elevates from mere camouflage to active psychological manipulation. The frogfish does not just wait for prey. It actively summons it, utilizing one of the most highly specialized and deceptive anatomical structures in the entire animal kingdom, the Elysium and the Esca. The Elysium is a modified dorsal spine that is migrated to the very front of the frogfish's head, extending forward like a biological fishing rod. At the end of this flexible rod sits the esca, a fleshy, highly maneuverable lure. But the esca is not just a static lump of tissue. Through millions of years of selective pressure, it has been sculpted and colored to perfectly resemble the preferred food of the frogfish's prey. Depending on the species, the lure might look exactly like a wriggling polychaete worm, a tiny, translucent ghost shrimp, or a desperately struggling small fish. Through incredibly subtle, calculated muscular control, the frogfish animates this lure. It twitches it, it jerks it, it creates the erratic, vibrating movements of a creature in distress. This introduces a layer of deception that operates in complete psychological reverse. While the massive, dangerous body of the frogfish entirely hides its identity, it simultaneously projects a false, highly visible identity outward into the water column. It becomes the invisible predator and the highly conspicuous prey at the exact same time. The Elysium acts as a hypnotic focal point. It draws the gaze, the attention, and the hunger of potential targets completely away from the massive, hidden structure of the frogfish's body. A passing predator, now acting as a prey, is driven by its own feeding instincts. Its brain locks onto the wriggling lure, isolating it as a vulnerable object. The approaching fish is so hyper-focused on the illusion of a free meal that it willingly swims directly into the strike zone, completely blind to the fact that the terrain around the lure is about to swallow it whole. And then comes the strike. What happens next is widely considered one of the fastest feeding events recorded in any vertebrate on Earth. When the prey crosses an invisible critical threshold, often mere millimeters from the frogfish's hidden lips, the predator initiates a catastrophic physical reaction. In a fraction of a millisecond, the frogfish rapidly drops its lower jaw and violently expands its buccal cavity. This massive, sudden increase in internal volume creates an immense drop in pressure inside the frogfish's mouth. It generates a localized, inescapable vacuum. The water outside the mouth, seeking to equalize the pressure, rushes inward with terrifying force, dragging anything suspended within it directly down the frogfish's throat. The entire sequence, from the opening of the mouth to the closing of the trap, unfolds in roughly 6 milliseconds. To put that speed into perspective, it is vastly faster than the prey's nervous system can even process the change in its environment. The prey's brain does not have time to register the shift in water pressure. It does not have time to send a panic signal to its muscles. There is no desperate thrashing, no opportunity for an evasive maneuver, no gradual escalation of a threat. The transition from the safety of the hunt to the darkness of the predator's stomach is instantaneous. The prey is relocated before it even knows it has moved. But this mechanism is not merely fast. It demands an excruciating level of precision. Because the frogfish cannot swim fast enough to correct a mistake, it must time its strike to absolute perfection. It must calculate the trajectory of the approaching fish, the distance to its mouth, and the flow of the ambient current. If it opens its mouth a fraction of a second too early, the suction field will fall short, and the prey will be pushed away by the bow wave. If it waits a fraction of a second too late, the prey may snatch the lure and dart beyond effective range. This mathematical precision requires a level of sensory integration, spatial awareness, and motor control that completely shatters the illusion of the frogfish as a simple, primitive lump of flesh. It is not reacting blindly to a stimulus. It is a highly tuned biological computer calculating, within the strict constraints of its neural architecture, the exact optimal millisecond to convert infinite stillness into absolute violence. Here, the narrative of the frogfish undergoes a profound philosophical shift. The frogfish is almost universally described as a master of invisibility, a predator whose entire existence is predicated on not being seen. But a deeper analysis reveals that its success depends equally, if not more so, on being noticed. Its strategy is not pure, absolute concealment. It is highly selective visibility. It meticulously hides a vast majority of its mass, the parts that would trigger fear, recognition, and escape. But it desperately highlights the tiny part of itself that triggers curiosity, hunger, and approach. In doing so, it hacks the decision-making software of its prey, guiding them, step by step, into a physical position where escape is no longer a physical possibility. This duality reveals a fascinating ecological twist. For the frogfish, invisibility alone is completely insufficient for survival. Without the lure, its perfect camouflage would be its own tomb. It would starve waiting for a random encounter. The frogfish must actively create a signal that overrides the natural caution of its prey. Its greatest weakness, its total inability to chase, is transformed into its ultimate strength by forcing the prey to cover the distance for it. The complete absence of movement becomes a stable platform for controlled, fatal attraction. However, this hyperspecialization comes with a tragic, inescapable vulnerability. The frogfish is entirely a captive of its own environment. Because its camouflage relies so heavily on mirroring the specific structures around it, it is deeply dependent on the presence of a healthy, highly complex reef. Coral reefs are characterized by incredible spatial diversity, countless hiding places, visual distractions, overlapping colors, and chaotic textures. In such a dense environment, the cost of constant vigilance is too high for prey fish, forcing them to rely on the cognitive shortcuts that the frogfish exploits. But when a reef degrades, when ocean temperatures spike and cause mass coral bleaching, stripping the vibrant colors away and leaving stark white skeletons, when pollution reduces the structural complexity of the reef to flat, algae-covered rubble, the frogfish loses its power. Without the chaotic, irregular textures of a healthy ecosystem, the frogfish can no longer assimilate. It cannot simply turn invisible in empty water against a barren backdrop. Its strange, lumpy body becomes highly conspicuous. Stripped of its living cloak, the invisible predator suddenly becomes exposed, moving too slowly to escape the larger predators that hunt by sight. Its strategy, while flawless under optimal conditions, possesses zero adaptability to a rapidly changing world. This leads to a deeply sobering narrative reversal. The frogfish, so often perceived as a self-contained, perfect killing machine, is in fact deeply, fundamentally dependent on the integrity of the world around it. Its invisibility is co-produced by the reef. The loss of that environment does not just reduce the frogfish's habitat. It mechanically dismantles the very biological system that allows the animal to exist. There is also a dimension of time to the frogfish's life that defies human understanding. It operates on a temporal scale defined by infinite patience. It may remain locked in a single position, perfectly motionless, for days or even weeks at a time, conserving its metabolic energy while waiting for the lure to do its work. This aligns with the extreme metabolic strategies of ultimate ambush predators, where the energy expenditure is dialed down to near zero between feeding events. The cost of this patience is a life of utter unpredictability. Success is never guaranteed. It depends entirely on a random movement of prey through the environment, the effectiveness of the lure, and the avoidance of larger threats. Yet when success does occur, it is so wildly decisive, so perfectly executed, that the massive intake of calories from a single instantaneous strike can sustain the animal for the next long stretch of empty time. In the broader context of the ocean's vast food web, the frogfish occupies a bizarre, almost contradictory niche. It is a terrifyingly effective hunter, yet it is also highly vulnerable to predation by larger, faster species. Its camouflage provides a formidable shield, but it is not an infallible one. Predators that hunt by chemical detection or electromagnetic fields can bypass the visual illusion entirely. The frogfish exists not as an untouchable king of the reef, but as a fragile participant in a deeply interconnected network of adaptations and counter-adaptations. And in the end, the most awe-inspiring aspect of the frogfish is not the record-breaking speed of its suction strike, nor the intricate, fleshy perfection of its disguise. It is the way it completely redefines the concept of danger in the natural world. We are taught to expect danger to announce itself. We expect it to move, to chase, to reveal its presence through the displacement of air or water. We equate lethality with kinetic action. The frogfish becomes the absolute opposite of this expectation. It proves that the most dangerous thing in the ocean is not the shadow moving toward you. It is a space where absolutely nothing is happening, right up until the exact millisecond that everything does. To understand the profound isolation of the open ocean, you must first strip away every instinct you have about survival. On land or even on the coral reef, survival is tied to geography. There are caves to hide in. There is kelp to weave through. There are rocks, shadows, and sand. There is a physical structure to put between yourself and the jaws of a predator. But out in the pelagic zone, the deep, open blue of the open ocean, geography ceases to exist. There is no floor. There are no walls. There's only an infinite, three-dimensional void. You are suspended in a desert of water. In this featureless expanse, the rules of life and death are governed by a single, unforgiving physical property: the transmission of light. Sunlight strikes the surface of the ocean and pushes downward, creating a massive, diffuse gradient. It is blindingly bright at the ceiling and slowly, inevitably fades as it penetrates deeper, shifting through a spectrum of brilliant azure until it is finally choked out by the crushing, absolute black of the abyss. For the creatures trapped in this middle space, the light is the ultimate betrayer. If you exist anywhere in this vertical column, you interrupt the downwelling light. You cast a silhouette. For the apex predators of the deep, the sharks, the massive tuna, the hunting marine mammals, this contrast is everything. They patrol the deeper, darker waters, pointing their highly adapted, hypersensitive eyes upward. They are not looking for the brilliant colors of their prey. They are not looking for the subtle, intricate textures of scales or fins. They are searching for the most primitive, inescapable optical signal in the natural world: a hole in the light, a dark, sharp outline moving against the pale blue glow of the surface above. In the open ocean, the silhouette is a universal signature of vulnerability. It is a beacon that announces your exact location to the abyss. And once that silhouette is locked onto, the chase is merely a matter of physics, muscle, and speed. Imagine a small, streamlined shape rising into that upward-looking visual field. Its outline is crisp, solid, and undeniable against the glow. A hunter stationed 300 feet below adjusts its trajectory. The predator's muscles tense, aligning its upward path with the dark, moving shape. The mathematical calculus of the kill has begun. The gap is closing. And then, without a single ripple, without a sudden burst of panic speed, the target simply dissolves. The prey has not moved out of the way. The predator has not blinked, nor has it lost its focus. Yet the dark shape is entirely, inexplicably gone. It is not hidden behind a cloud of silt. It is not obscured by a passing wave. It has been completely erased from the only optical perspective that matters. This is a squid, and its mastery of survival is not built on blending into a physical environment. It is built on actively, mathematically rewriting the very light that defines its existence. To survive in a world where casting a shadow is an automatic death sentence, the squid has evolved to break the fundamental laws of optics. It achieves this through an astonishing biological process known as counterillumination. The squid does not try to hide its physical body. Instead, it aligns its own biological light emission with the ambient light field of the ocean, embedded in the skin of its ventral surface. Its belly, the side of its body that faces the terrifying, upward-gazing depths, are thousands of highly specialized, complex organs called photophores. These are not simple, glowing patches of skin. They are sophisticated, microscopic biological floodlights. Each individual photophore is a marvel of living engineering. They contain a light-producing chamber filled with specialized bioluminescent bacteria or complex chemicals that react to create a cold fire. But the hardware goes much deeper than just producing a glow. These tiny organs are equipped with cellular reflectors to direct the beam outward, living lenses to focus the light, and biological color filters to perfectly tune the wavelength. The squid is not simply glowing in the dark. It is projecting a highly calibrated image. When the predator looks up, it does not see the dark, solid belly of the squid blocking the sunlight. It sees the light produced by the squid's photophores. The goal of the squid is to exactly match the brightness, the intensity, and the specific blue wavelength of the downwelling sunlight. If it projects too much light, it will look like a glowing neon beacon against a dim background. If it projects too little, it will still cast a faint gray shadow. The output must be flawless. It must perfectly equalize the contrast, essentially filling in a hole in the light that its physical mass creates. When this delicate process is executed correctly, the squid's body becomes visually neutral. It cancels out its own silhouette. To the eye of the predator looking up, the squid simply looks like more of the endless, glowing ocean surface. The animal occupies physical space. It has weight. It displaces water, but it completely fails to register as an optical object in the predator's brain. This strategy represents a fundamental shift in the nature of concealment. Traditional camouflage, like that of a flounder on the sand or a moth on a tree trunk, relies on matching a background. But in the open ocean, there is no background. So the squid does something that borders on miraculous. It manufactures its own background. It creates a localized artificial version of the sky, effectively carrying a piece of the light field with it wherever it swims. It is not adapting to the environment. It is generating a localized version of it. But the sheer computational power required to maintain this illusion is staggering. The ocean's light field is not a static painting. It is wildly, chaotically dynamic. The intensity of the downwelling sunlight changes with every passing fraction of a second. It changes as the sun moves across the sky from dawn to dusk. It changes dramatically when a thick cloud rolls over the surface of the water miles above. It changes depending on the turbidity of the water, the density of the microscopic plankton drifting through the column, and the angle of the surface waves refracting the light. And critically, it changes with depth. If the squid swims 10 meters deeper, the ambient light becomes darker, and its photophores must dim instantly to match. If it ascends, they must brighten. To manage this impossibly complex optical environment, the squid must operate as a continuous, real-time biological feedback loop. It uses its large, highly developed eyes, some of the most advanced visual organs in the animal kingdom, along with specialized extraocular light-detecting organs located on top of its head, to constantly measure the exact intensity and wavelength of the light coming down from the surface. Its advanced nervous system processes this incoming data and instantly sends electrical signals to the thousands of photophores on its belly, commanding them to adjust their output. The squid is constantly measuring the sky and adjusting its underbelly to match. It is a living mirror, reflecting a sky it cannot even see. From the perspective of an enemy it does not know is there. Yet, this spectacular system is not purely defensive. It is not just a shield against the horrors lurking in the deep. It is also one of the most terrifyingly effective offensive weapons in the pelagic zone. By eliminating its silhouette, the squid can approach its own prey from below without triggering the deeply ingrained escape responses that keep small fish and crustaceans alive. The tiny organisms that the squid hunt are just as sensitive to shadows as the massive predators that hunt the squid. A small fish looking down into the abyss expects danger to arrive as a dark, expanding shape rising against the deep blue. The squid completely bypasses its detection system. It ascends into the prey's field of view not as a creeping shadow, but as an absolute absence of signal. It looks exactly like the empty, glowing water it is displacing. It closes a vertical distance, rising like a ghost from the depths, completely unperceived by its victim. When the precise moment of attack arrives, the squid transitions from perfect, glowing invisibility to explosive kinetic violence. Tucked away within its ring of arms are two specialized, highly elastic feeding tentacles. These tentacles are equipped with gripping clubs covered in toothed suckers. Driven by a combination of rapid muscular contraction and internal hydraulic pressure, these tentacles shoot outward with blinding speed. They extend, grasp the unsuspecting prey, and retract in a fraction of a second, dragging the struggling victim directly into the center of the squid's arms, where a razor-sharp, parrot-like beak waits to tear flesh from bone. The entire success of this brutal strike depends completely on the proximity the squid achieved through its counter-illumination. Without the ability to approach completely undetected, the squid would be forced into an energetically costly, high-speed pursuit in open water, a chase that would burn precious calories and risk drawing the attention of larger predators. Here, the narrative of the squid begins to fundamentally invert. The reliance on delicate light manipulation initially suggests a purely defensive, fragile adaptation, a desperate means of avoiding detection in a terrifying, featureless void. But in practice, this fragility is weaponized. It becomes a deeply offensive tool, enabling the animal to occupy a position directly beneath its prey without generating a single alarm. Its greatest weakness, the absolute lack of physical cover in the open ocean, is completely transformed into its greatest strength through a mastery of bioluminescence. The absence of physical hiding place becomes totally irrelevant when the animal is capable of generating its own optical concealment out of thin water. This introduces a profound ecological twist. Invisibility in the open ocean is not about hiding from view. It is about controlling the very conditions under which viewing occurs. The squid does not remove itself from the visual field of its enemies. It alters the structure of the field itself. It ensures that its physical presence simply does not generate the specific optical cues that the predatory brain requires to trigger recognition. However, playing God with the physics of light is an exhausting, dangerous game. The metabolic cost associated with maintaining this illusion is immense. Producing biological light requires a continuous supply of chemical energy. Maintaining a flawless, continuous output of light across thousands of individual photophores over extended periods is incredibly demanding on the animal's reserves. The squid cannot afford to glow simply for the sake of it. It must carefully balance the life-saving benefits of invisibility against the staggering energetic costs of maintaining the machinery. It must constantly calculate the risk. It deploys its counter-illumination most actively when it is in the twilight zone, the mesopelagic layer of the ocean where downwelling light is faint but still present, and silhouettes are at their absolute deadliest. This introduces a strict temporal dimension to its behavior. Periods of highly active light production are interspersed with intervals of darkness, perhaps when descending to the absolute black depths where silhouettes no longer matter, or ascending to the surface under cover of a pitch-black, moonless night. Furthermore, the effectiveness of this strategy is entirely dictated by the clarity and structure of the surrounding light environment. In perfectly clear water, with strong, undisturbed downwelling sunlight, the contrast between an object and its background is sharp and unforgiving. Here, counter-illumination is absolutely vital, but it is also the most challenging to execute perfectly. Conversely, in highly turbid, cloudy water, or during twilight, the light gradient becomes diffuse and muddy. The need for precise high-definition light matching is reduced, but the photophores themselves become less effective at piercing the gloom. The squid must operate within a constantly shifting set of environmental constraints, continuously adjusting its physiology to maintain the razor-thin margin of optimal concealment. This absolute dependence on the external environment leads to a second narrative reversal. The squid, so often perceived as a master of its own visual destiny, an active creator of its own invisibility, is in fact deeply constrained by the unpredictable variability of the ocean's light field. Its ability to disappear is not a permanent, absolute superpower. It is highly conditional. It is shaped, limited, and governed by atmospheric and oceanic factors far beyond its direct control. The ocean provides a grand template of light. The squid merely provides a desperate adjustment. Beyond counter-illumination, the squid possesses additional, highly advanced capabilities that enhance its control over its visibility. Its skin, much like the cuttlefish and the octopus, contains millions of chromatophores and reflective cells that allow for rapid, instantaneous changes in color and pattern. In combination with its bioluminescence, this creates a multi-layered system of camouflage that can operate across a vast range of optical conditions. The squid is not limited to a single strategy. It can switch between modes, selecting the exact approach that best fits the geometry of the immediate threat. In the broader context of the marine food web, squid occupy a massive central pillar. They are both voracious, highly efficient predators and the vital prey base for some of the largest creatures on Earth. Their ability to mathematically manipulate light directly influences their survival rate on both ends of the spectrum. By reducing their visibility to predators, they persist. By reducing their visibility to prey, they consume. This dual role wildly amplifies their impact on the global ecosystem. Any shift in their behavior or abundance ripples immediately up and down the trophic levels of the ocean. And yet, despite all of this optical perfection, the squid remains profoundly vulnerable. Evolution does not allow for a permanent victor. While the squid has perfected the art of defeating the eye, many of its greatest predators have simply stopped looking. Sperm whales and deep-diving beaked whales plunge in the abyss to hunt squid not by sight, but by sound. They emit powerful, deafening pulses of biological sonar, echolocation clicks that rip through the water, bouncing off the dense internal structures and hard beaks of the squid. To a hunting sperm whale, it does not matter how perfectly the squid matches the downwelling light. The whale is not looking at the light. It is listening to the physical density of the animal's flesh. Against the acoustic mapping of a whale, the squid's glowing belly is entirely, tragically useless. Counter-illumination is an absolute defense, but only within a specific, visual sensory framework. It is a brilliant answer to a specific question, But the ocean constantly changes the question. The squid exists within a vast, three-dimensional network of interactions where no single adaptation guarantees safety. In the end, the most awe-inspiring aspect of the squid is not the microscopic complexity of its light-producing organs. It is not the computational speed of its neural feedback loops, nor the precision of its explosive, tentacled strikes. It is a profound philosophical statement it makes about reality in the open ocean. It proves that light, the very medium that exposes, reveals, and endangers, can be bent, hacked, and weaponized. In a world where being seen is the ultimate determinant of life and death, the squid does not waste its energy trying to avoid visibility. It does not cower in the dark. It captures the light. It calculates it. It replicates it. And then it uses it to completely erase the very conditions that make visibility possible. The history of our planet is written in the shadows of the past, buried in deep time and waiting to be unearthed. But the story is far from over. If you want to journey deeper into the untold histories, the prehistoric mysteries, and the epic forces that shape the world we live in today, make sure to subscribe to Earth's documentary. Hit the bell icon so you never miss a chapter of our planet's most incredible narratives. We have massive new deep dives on the way, and you won't want to be left behind. Subscribe now, and let's keep exploring the greatest story ever told.